So my name is Professor Ved Chirayath, and I'm the Vetlesen Professor of Earth Sciences, Aeronautics, and Mechanical Engineering at the University of Miami. I direct something called the Aircraft Center for Earth Studies, and I'm a National Geographic Explorer. Oh, I have kind of the dream job. I had worked at NASA for 10 years, and I have basically the same job here now with a lot of the same NASA grants and projects. So one thing I'm really excited about, I actually brought with me, is Oceans Across the Solar System. This is a new initiative that's trying to merge a lot of the knowledge that there is at NASA from planetary science, the search for life beyond Earth, and our knowledge of Earth systems and the oceans, and basically the only example of life we have in the universe. So I'm really passionate and excited about exploring our homeworld to try to better understand and inform the search for life elsewhere. And in that process, I've become, I went from being an astrophysicist and a theoretical physicist to an oceanographer. And I primarily develop new technologies and instruments for NASA, NOAA, and other places to study the ocean floor, to map it, to essentially fill in the gaps of knowledge we have, which for the ocean, it's quite startling. You know, we've actually, coming from astrophysics, and one of the reasons why I moved into oceanography is that we've mapped more of the surface of Mars and the Moon and even the Sun than we have of our own ocean floor. One of the projects I'm leading is a global effort to automate the coral reef detection of organisms and change over time. So just like we study on Earth's land, you know, how crops are changing over time or how forest areas are changing, we don't have any of that kind of knowledge in the water just because there's no baseline mapping data. So a lot of times we'll go to an island, we'll map an entire coral reef, and then we'll return every year and do that again and again so that they can look at what's changing in the environment and sort of come up with a census for that coral. And then they say, okay, you know, this one's doing well, it's recovering, or this one got hit by a marine heat wave. We need to reduce some pressures on it to help it recover itself. That model's worked very well, except it's sort of based on this parachute science model of, you know, someone will come out, they bring these technologies, they do the science, and then they share the results with the community. But in all of the best kinds of science conservationist engagement that we've seen, the long-lasting efforts involve the local community at a grassroots level. So what we're trying to do right now is launch a global 4-year effort to, and we've done this in Guam successfully with another NASA grant. Train in Guam, we trained 25 local pilots. So these are students who had never flown a drone before. We gave them advanced drones, we flew them like sensors, and said, okay, we're going to train you and pay you every year, you know, to go and map your own reef and preserve it. And the minute that you get local folks involved in their own conservation, then they see for themselves, this is what the reef looks like. This is the reef that they depend on. They're invested in protecting it, and they produce the data sets themselves. They have sovereignty and ownership over it, and it completely changes the paradigm from this parachute science model to a capacity building, you know, indigenous community model where we are sharing that knowledge and they're sharing the data with us. Actually, they're very similar in that both of them work in an environment that's hostile. You know, it's not a great place to be, cold on top of a mountain if you're an astronomer, or seasick in the middle of the Pacific, you know, if you're an oceanographer. And then they both, what I deal with a lot is remote sensing. So trying to study these environments without touching them from afar. And astronomers are very good at not touching things, mostly because they can't. So they get all the information they can from light, right? And light has so much information in it. Just from this image, right, you can tell I'm human. Hopefully there's a chair, right? There's materials, there's colors, there's spectra that tell you information about what I am and what this is. We use that same information with telescopes to look out at the universe. And then with satellites and aircraft, we look down at Earth and try to assess the same information. But the challenge is always in water, it's dark, right? It gets really dark really quickly. And that for a lot of oceanographers is the end of the story. And for me, it was like, well, in astronomy, all you work with are things that are dark, right? You're working in this limit of tiny amounts of light. And astronomers are not shy about building very large space telescopes to solve the problems of this darkness, right? To try to gather as much light as they can to detect something and pull it out from, you know, nowhere. And I think as oceanographers, we should adopt that same philosophy. We're looking at the ocean like humans do, and we need to be looking at the ocean like animals in the ocean do, with massive eyes, right? Big optics, things that can see very, very deep in the water, because it's there to be gleaned. It's just a matter of will. Just like astronomers, dreamed up the James Webb Space Telescope, and the OWL was one of my favorite, the Overwhelmingly Large Telescope. All of those telescopes started as this is what the physics is saying we should do. And in oceanography, I've made a career of saying, well, the physics demand this, and so I'm going to invent an instrument that can do that. One example I like to share is, this example of parrotfish. This is an organism called a parrotfish, very pretty looking thing. Happens to also be very delicious, so people eat them a lot in the Caribbean. And a lot of the Caribbean coral reefs, as a result, are in a poor state. They've collapsed. And in a few cases, in Bonaire, for example, they had tested what it would happen if we did not harvest parrotfish. So the fishermen were told, okay, you can go after different things, but let's try to let the parrotfish recover to see if it has an effect on the coral reef. And the entire coral reef ecosystem recovered because these guys were going around cleaning the coral from algae and helping it recover. And then as a result, the fish stocks of everything else went up. And so it was an example of having a little bit of knowledge of how that interconnectedness works, and then using it to say, okay, I'm going to create a conservation solution that doesn't change the fundamental culture of this place, but allows the natural system to recover itself. I hope that people, if they want to understand their world and how animals live, they should go out and make animal friends and try to understand and live in their environment and see it for themselves. And I had one of the other experiences I had on one of my field missions was it was a couple of months long in American Samoa, very far out in the Pacific. And every day I was on the reef, moving an instrument back and forth. And there was this little thing in the corner of my eye. I just kept feeling that was there. And only in like the fourth week did the octopus finally let me see it. And it was this little baby octopus that had been coming and looking at me at the same time I went out each time. And over the course of the next month, it would come closer and closer, eventually like touching the camera and the instruments I was using, my hand, and trying to figure out like, who are you? And like, what are you doing in my reef? And it was just so inquisitive. And I think what's exciting about getting to be an oceanographer and somebody who, I just was honored to be one of the 30 finalists for the astronaut corps. One of my main goals for being an astronaut was to try to understand, can we find life elsewhere? Can we understand what other worlds are to inform that search for life? And here in the ocean, you get to have this eye-to-eye look with another creature and see that it is sentient, and then realize that it's looking at you and asking the same question, and that's just, for me, the most mind-blowing experience beyond stromatolites and corals, is just getting to be in an environment where animals regularly look at you and recognize your sentience, and you get the opportunity to look back at them and see the same thing and realize, oh my gosh, this is really just one little planet, and we're all kind of getting along together, for better or for worse. Sure. So NASA's been super supportive of encouraging my basically Star Trek ideas, trying to apply them to sensing on Earth. So again, the ocean is dark, right? So that was my first challenge, and I spent my PhD trying to develop a way that can see deeper in the column of water, as well as see through ocean waves, which blur and refract what you're looking at. So that technology, fluid lensing, is now, works very well, and we've done it at global campaigns to map coral reefs. We find all kinds of things in those reefs, right? So if someone drops a cell phone or like a tire, it's like you're mapping like the planet for the first time and seeing down to 65 feet. There's more surface area of planet in that first 65 feet than there is land. So it's just like every time we look at a new data set, we're seeing new organisms, new coral structures, new marine debris. We just did a campaign in Guam, which got hit by the typhoon, and the corals were protecting the island massively. And that became clear when we started looking at the corals and how much of the hurricane they took on. The second technology I had invented at NASA, something called MIDAR, takes this the next step. So it adds active laser sources and light emitting diodes to basically shine a light deep down from aircraft or from spacecraft into the ocean to see deeper. And what's really exciting, I think, is we're now at this precipice of understanding the ocean the way that animals that live in it do. So most animals in the ocean, they communicate, again, through bioluminescence, so through color. Then there's also acoustics. So we've been studying the ocean acoustically. What we're doing with MIDAR right now with a new NASA grant is mapping the ocean in the ultraviolet and the blue wavelengths. So when you go down deep in the water, first it starts getting darker and darker, then it starts getting very, very blue, because most of the longer wavelengths of light, like red and green, they're all scattered or absorbed. And when you get down to about 65 feet, 75 feet depth, it's basically only blue, and then there's all these colors in ultraviolet. But humans are not designed to see them. We can see blue a little bit, but really it's, it just looks blue. You cannot see ultraviolet at all. And ocean animals can. So what MIDAR is capable of doing is revealing some of these ocean environments for the first time in ultraviolet and blue. And we look at not just at, one color, we look at 13 different colors in the ultraviolet and blue to get sort of the James Webb Space Telescope view of what the seafloor looks like. And it turns out that it is just wild. It's like looking at the ocean as if it were Avatar film, Pandora, you have these bioluminescent creatures and seas. That's what the ocean looks like to most sea creatures, and we're just for the first time seeing it the way they do. And that means that when we look at coral now, it's not just a green or red or brown blob. It has these 13 different colors in the ultraviolet, and they're neon colored, and they've got these striations, and a lot of the diseases that they're facing, which are hard to detect, are easily visible in ultraviolet. And so that's one of the main reasons and efforts I've been doing, is trying to shift our attention from, we've been imaging the ocean like we've been imaging land. And on land, we're perfectly evolved, right? We evolved on land. So we see in colors that on land are omnipresent, red, green, blue. In the water, we're terrible, right? You go down deeper than 80 feet and it's dark and we're blind, and fish can still see at those depths. So they're doing it because they're looking at the right colors. And I think that's one of the main things I'm very excited about, is to see us looking at the ocean that same way. And then what's that going to allow us to understand about the sea as a result. Yeah, I mean, never lose that curiosity. I still feel like the 5-year-old kid, we're coming to work and getting to see things for the first time. That never gets old. Science is not easy, and being someone that was a lifetime Trekkie and getting inspired by the discoveries they're making, what they do not show you in Star Trek is that science is a lot of drudgery, right? It's a lot of failing and spending tons of money and not getting a great result, and that's okay. And you can get through these things if you can start learning how to build really good relationships with mentors and peers, and learning from them, sharing in the failures when they happen, creating an emotional support group. I think one of the nice things, and then there are a few, of being someone that identifies as LGBT is you learn to create, a lot of cases your family will cut you off and kind of disown you or separate yourself. That support network that you grew up with is essentially pulled away from you. And so you're forced to create your own family, your own support network. So I encourage a lot of people to remember that you've got to have grit, perseverance, a lot of charm, and patience to get through something. Intelligence helps, but some of the best scientists I've seen are folks that just do not give up. They're passionate and they want to answer a question, and they pursue it no matter what. And I'm so lucky to have, all along my career, people that believed in me, that supported me, and a lot of allies that were not LGBT, that, and I'm one of the only people in my field that identifies this way. And I'm certainly, when I go to conferences, generally the only person. I'm lucky that that's changing. But, those are folks that recognize you're going through something difficult and are sticking their necks out to say, hey, I support you. Even though I'm not part of this minority group, I will do that. And I had mentors at NASA, throughout academia, in high school, all of these different levels that were fundamentally instrumental role models in making me who I am today. And then you get older and you realize I now have to be this person to the next generation, right? And so now I'm trying to do as much of that as I can to tell other people, look, you can do it. I've gone through this as well, but you'll have support and people believe in you.